Hello Professor, this is Hussein Lausi and my partner Alia Sheikh. Today we're going to present for you the final project for the introduction to autonomous vehicles, and our project name is Path Following Control Using PID. So I'm going to start with the introduction. First of all, we need the autonomous vehicles for main two reasons: increase the safety of the traveling system, and the second thing is make it more convenient and relaxing for the customers, and helping by providing them more time to spend on other things like studying or relaxing or other kind of stuff. The growth of the sensor technology help us improve the autonomous vehicles by having a high density lidars or very good resolution cameras. Also that will help make the lane detection easier for us to deal with. Also on this project we're going to use the lane switching with the Bezier curve dynamics in order to get an estimated route to follow between one lane and another. Now I'm going to talk about the objectives of this report. First, we start with building and simulate the environment that we're going to use for testing and validate our system, and then generating the middle lane that we need to let the car follow it, and then apply the PID to make sure that the car will follow and stay in the center of the middle lane that we just generated. Then we're going to add the Bezier curve and apply PID controller to make the car follow that Bezier curve. Now the system overview, as I said, we're going to start with the simulated world, and then we have a camera and the LiDAR sensors that we're going to use in this project, but we delayed the LiDAR to the future works, and then we're going to see why at the end. Then we enter to the perception algorithms about using the camera to provide the data that we're going to use to have the lane detection. And our main goal is to build the lane keep control algorithms, which is separated into two sub-main goals, with the lane centering and then the lane changing. For the lane centering, we use the PID control to control the car on it, and then we used for the other point Bezier curve, and both of those two main points was providing instruction to the steering throttle and the brake to control the car. This is our testing environment that we're going to test our system with. We have a straight line here, and we have also a double lanes to test the changing lanes. We also have a entrance curve and leaving the curve to see how the car will do on the curves also. This is the first step in our project, which is generating the center lane. The red lanes and all these data is represented in the vehicle frame. The red lanes is provided by us by the previous generated code by the IGBC. The green lane is represented by our work, the beginning of our work. The middle center point of the rear axle of the frame represent the 0, 0. We have this, the positive Y, and we have in front of the car the positive X. So by adding the Y's of these 2 points, we're gonna get the first point, and then keep doing that we will get the green center middle lane that we need the car to follow. Our control system is trying to minimize the lateral error, which is what we can see in the yellow arrow, which is literally just trying to align the blue estimated line, which is not really generated by the system, with the green line, which is represent the generated center line, by just subtracting the first point of the Y of the generated center line from the Y of the actual footprint of the car. So when we first start testing our car, it was running perfectly when the lane was straight, but we start seeing a problem once we enter the curve. As you can see, the left rear tire is stepping on the middle of the lane, which is violating the rule of staying in the middle of the lane. This problem was caused because the first point that we are trying to follow is relatively far from the vehicle itself, because the center point of the car is, as I said, in the center of the real axle, and the first point is 5 meters ahead of them, the vehicles. So in order to solve this problem, we came with two solutions. The obvious solution was to tilt the camera in order to get an earlier point closer than 4.7 meters in front of the car. But as you can see here in the video, the camera is already tilted to a degree that the hood is start showing up in the frame of the camera, so we cannot tilt it anymore. So the first actual solution that we tried is we already have the actual points that's coming from the generated center lanes, but we need an earlier point, so we use the least square estimated algorithm to generate an estimated points in the front of the car. As we can see in the video, we have a center line that we could follow, but it has two problems. The first problem, as you saw, it's kind of going back and forth, so it's not stable. And the second problem is, as you can see, it is tilted. It is not correctly into the center of the car, so we cannot use this solution. So we came up with another solution, and my partner Ali will take.
Hello everyone, this is Ali. So in order to solve the problem, the curve issues problem, we don't have to predict or estimate the center line. Actually, there is another way to solve it, which is so we can actually use or memorize the center lanes that we generated in the past before we reach this point. So we can use those lanes in order to use it at different times. So for example, here in the picture, the detected line is actually from here to here, right? This is what we detect after 5 meters from the footprint, but we can actually combine this with what we saw or what we generated like 3 seconds ago, or sometimes in the past. We can actually combine the one that we generated a time ago plus the one we detecting right now with the camera, and then we will follow the first point in this, which this will eliminate the problem of following a point that is far from the car. So how do we do this? So first of all, as Hussein said, everything here is in the vehicle frame, right? And by vehicle frame, when the car moves, the vehicle frame changes, right? So we cannot actually store the past points in the vehicle frame. You have to convert it to global frame to be able to use it at whatever time or whatever position the car in. We just have to reconvert it to vehicle and use it at that time. So the algorithm stays like this. First we convert the generated center line to global frame, and then we added or concatenated with a variable called like all center lines. Second, we convert this vector, the resultant vector, to vehicle frame in order to find, for example, the problem is now, if we keep adding a new center lines, we will have many points, right, in this vector. So we need a way to sort it, right, which one to use. So what we need is, at this point, like for example this time, we need the points that are here, right? We need these points that are very, like we have a look ahead distance, and we need a point here. We won't need those points of the center line, right? So we have to sort it. So we find the point that is, the x value is the closest to the look ahead distance, which is a variable we change, depends on where do we want. So we have here the point start from. So here we have it at 5, here at 4, here at 3. So here at 3, the look ahead is the 3 from the footprint. So that's why I start from here. And then we pass this point, this one, to the PD to control, and to visualize it, we pass it to Arvis. So now that does help us maintain the car in the middle in the curve, but we got a new problem, which is when the car trying to finish the curve is very sharp. So at some point, while the car is nicely placed in the middle, at some point the camera loses the other line here. It only detects one single one, so we cannot drive because now we cannot generate a middle line, so we cannot feed anything to the control, so the control system stopped, so we cannot continue like this. So we had to find a way to like trade off between not allowing this to happen and violating the center line like by a bit. So our best, so how far the first point of the line, center line, is controlled by a CFG variable, which is the look ahead. So the best look ahead, so this problem happened when the look ahead is 3 or even 4, but with 4.3 we got the best performance. So now for lane changing. So the lane changing is very important for the IGVC because for some courses we are required to change the lane when there is something like construction barrel in front of the car. So in order to change lane smoothly, we need to generate a path that smoothly the car will follow in order to change lane. And we chose to use Bezier curve equations in order to generate this line. And as you can see, we used 4 points. Those 4 points, the first 2 the car will hit, and the second 2 will affect the way of the start point and like the direction or the slope of the Bezier curve. So if you can see here, it's very smooth curve. This is like the first advantage. The second one is at the end of the, like here, at the end of the Bezier curve, you will notice that the slope or the direction of the last point of the curve will be parallel to the tangent, like this one. This is very, very good for us because this not only will make sure that the car, when the car is finished from changing lane, it will be in the middle, but also the direction will be parallel to the lanes, which is maintain a stable lane switching. So here we have those 4 points. We have, if you notice, we have 2 in this lane, and we have another 2 in the middle of the next lane, and this is the curve. This is, so those 2 tangents are only for visualization here to illustrate how it works. So now, after we generated it, we need to follow it, and actually only generating is something and really making the car follow it, and at the end switch to lane keeping mode is something totally different. So in order to, as we said earlier, everything is in vehicle frame. So the problem is, if we generate it in vehicle frame and keep it in vehicle frame, the problem will be that when the car is trying to move to the left, the whole path will also move to the left. So the car will be rotating, trying to finish it, and the curves keep moving. So we need to generate it at first in the vehicle frame, then we will convert it to global and store that value, and then at each time, because the cars keep moving, the global frame keep changing, at each time we keep updating the path from the global frame to the new vehicle frame and publish it for visualization. And then, okay, so now we have a fixed like Bezier curve we need to follow. The problem is now, how do we follow it? So we generated like 100 points for this line strip to be visualized. So we have 100 points, but which point do we follow at each time, right? And how do we know that we are done with the Bezier curve? Let's now start following the lane, so we continue to complete the course. So first, we find the hypotenuse for each point, which is x squared plus the square root of x squared plus y squared for each point from the car, okay? And then compare this to some look ahead distance, which is 2 meters. We are trying to follow the points that are within the Bezier curve and 2 meters away from the car, and we keep following this until we reach a point that we don't have a point that is greater than this 2 meters, and at this point that's the indicator that okay, we finished the Bezier curve and there is no points away from us. So now let's change to lane keeping mode. So now it's time for a demo. So our control system was tested using 2 courses. This one, the Q2 course, and one that we made ourselves. So as you can see now, I will hit the turn left in order to change lane. So for now, this is our indicator, but actually we are required to use YOLO or machine learning to detect this, and based on this we have to change lane. So as you can see, it did turn to the left, and then now it's lane keeping mode. This is the first test, and this one is the second with the one that we made, where there's a curve and there is straight line and then curve. You can see there is actually a little bit of stepping on this line still. But like if you can see here, any correction to the right a little bit, we will lose this line. So this is the only one we are detecting right now. So any correction to the right in order to maintain lane keeping will make us lose this, and we will stop. The control system will stop, because with only one we cannot generate anything. So like we definitely needed a wider angle camera in order to manage this very perfectly. Okay, we will see this in a better way in the next slide. Yes. So now for results, this is our error. We only used PD controller, was fair enough. And we have the time here. The time actually doesn't matter, it depends on how fast my computer get to everything works in the launch file. So we have this here. So we tried to change the P. So like if you can see here, there is this movement that's not that we don't like it. It's not very good. So in order to minimize it, we thought, okay, let's decrease the P. But the problem is when you decrease the V, we have this, it's kind of less zigzagging performance, but the problem is at some point we do like, okay, so this is the straight line in the road we made, first straight line and then curve. So in the curve it's very nice, but the problem is at some point we lose the 2 lanes, we lose one of them, so the control system stopped, and you see this steady because the P was very low. So we had to increase it in order to finish the whole course. So purposely we made it spawn the vehicle from a very like not centered location, so the car will correct itself to go to 0 error, and then finish the straight road, and then the curve, and then back to the straight. So you can see the changes in the error curve based on the P and the values. And then now back to Hussein.
So in conclusion, we developed a project that used lane centering, and the car was able to drive in the middle of the lane using a PD controller. We start by taking the IGVC course, startup code, and then we start generating the middle centered lane that the car need to follow. And then we add PID controller to make sure that the car stay in the middle of the lane. Then we use a Bezier curve and follow that by PID controller to make sure that the car will follow the curve generated. All in all, we were able to let the car drive successfully in the center of the lane and remain in the middle of the lane, and also able to switch the lane safely without an error. The control algorithm was used to validate our system, was based on the different scenarios, and however the PD, the last thing I want to say, however the PD was good enough to finish the course, but the PD controller was not able to let the car stay on the steady state error or at the zero level of error. So in our future works, the first step we're going to do is either adjust the camera extrinsic characteristic or use a wider angle camera, so in that case we will not lose the lane under any situation. The second thing is we're going to use like the single input multiple output control system PID rather than using two PID for doing two things. Or the next step is add an improvement for the car by using an MPC control, model predictive controller, because that will help us include all the dynamics rather than stay limited. What I mean by that is when we are trying to change the speed right now, we need a new control system because we did not include the dynamics of the system. Also integrating the YOLO with our system and let it be the triggerer of the lane changing. Right now we are using the CFG. Using a LiDAR to check the other vehicles on the other road or on the before switching the lane. That would be a safe point. And these are our references. Thank you very much.